Attendees are in listen-only mode.
Good morning, everyone in North America, and we have a few people from Asia, actually, so good evening to those people. This is about chemical contaminants in food. Do we really understand the details of hazards in food, chemical hazards in food? That's the topic, actually. Okay. A food safety hazard is anything present in food with the potential to harm the consumer either by causing illness or injury. Food safety hazards can be biological, chemical, or a physical object. So, good food safety practices must be science-based, and therefore, a thorough understanding of hazards is the first essential step in the control. You'll agree with me on that. The presence of chemical hazards in food, I'm just changing slide. I'm on slide 2. The presence of chemical hazards in food is usually less apparent than that of bacteria, or for that matter, other biological hazards. Acute toxicity caused by foodborne chemical contaminants is very rare these days, but still it does occur once in a while. The concern is exposure to low levels of toxic chemicals in the diet over long periods. So that's the main concern, that is low levels of toxic chemicals in food is indeed a concern. So in some cases, this can lead to chronic illness, and there is also the risk that some contaminants may be carcinogenic. This webinar will provide important information on chemical hazards that are required to support the development and understanding of hazard-based food safety controls. It addresses the main categories of chemical hazards associated with food and the toxicology of these hazards. So this information can be used to assist in the development of more robust hazard plans. We all know the Codex model of hazard requires identification of chemical hazards during hazard identification and risk assessment stage. Chemical hazards can come from a variety of sources. These can be internal, from within the food processing business itself, and external, associated with environmental and naturally occurring sources. On occasions, they can be intrinsic to the food itself. Now, we talked about internal, external, but it could also be intrinsic, coming from the food itself, and also intentionally added as part of the product formulation. While many of these hazards and sources can be relatively easy to identify, it's common for many hazard teams to overlook it. And generally, I think people overlook chemical hazards or incorrectly risk assess these chemical hazards. Why? This is often due to the poor understanding of chemical hazards and also the science of toxicology and the mechanisms behind the effects of chemicals on the human body. So these are some reasons why people fail to identify chemical hazards in the hazard plan. Toxicology. So before I get into the details of chemical hazards, let me just take you through the basics of toxicology. Simply defined, toxicology is the science of poisons. When it comes to chemical hazards and food safety, an understanding of toxicology is really helpful in conducting risk assessments and developing food safety controls. It really helps. In general, it is a study of harmful interactions between chemicals and biological systems. So what is biological system? Your body is your biological system. So interaction between chemicals and your body system is a study of toxicology. The origin of these chemical substances can be from several sources. It could be from drugs, pharmaceutical drugs, pesticides, industrial chemicals, and could also be from food additives, and could be from natural sources as well. Let me differentiate between acute and chronic toxicity. So in this slide, I would like to define the two most often used terms in toxicology, acute and chronic toxicity. Acute toxicity is defined as an immediate toxic response, instantaneous response, whereas chronic toxicity is defined as the toxic response that appears over a long period of time. It doesn't kill immediately, but it produces a result over a period of time. So that is chronic toxicity. Example of acute toxicity is accidental poisoning of human beings by ingestion of insecticide. And an example for chronic toxicity is slow poisoning of human beings by ingestion of, say, arsenic. Okay, you are all familiar with that. Now, dose-response relationship. The fundamental principle of chemical toxicology are, the principles are based on dose and response. Basically, it is a relationship between the level of toxin and the adverse response arising from the dose. For many people, for many individuals, there is a dose level at which there is no observable response. Okay, you don't come across any response until a level is exceeded. Okay, this is known as NOEL, NOEL, which stands for no observable effect level. Above this level, the effects will be observable, and that's what I mentioned to you just a few minutes ago. And this relationship can be shown on a dose-response curve as shown on the slide. Okay. A common measure is LD50. Some of you may be familiar with the concept of LD50, which is the lethal dose that produces death in 50% of exposed organisms. The concentration that will produce 50% death in a population of animal is known as LD50 value. Okay. It's commonly used in toxicology. Okay. Generally, this data is derived, for human beings, the data is derived from animal data. I know this is somewhat crude, but that's the only way you can test the LD50 levels, and you have to extrapolate the results obtained from animal studies to human beings. In the next slide, I am going to give you some examples of LD50. Okay. Common salt, let's take common salt. We use that every day, and it's lethal at, say, 40,000 milligram per kilogram of body weight. This is essentially for rats. You know, people have done a lot of experimentation, and they came to the conclusion that sodium chloride or common salt is toxic at this level. Okay. Whereas look at botulinum toxin. You know, toxin produced by a microbe, Clostridium botulinum, which is extremely lethal, and it's lethal at 0.0001 milligram per kilogram body weight of rats. Okay, this is all for rats, and these values, these numbers are based on experimentation, and they're well documented. Okay, and the results become somewhat blurry when you try to extrapolate to human beings. And obviously, we cannot do this kind of experimentation directly on human beings. We have to depend on animal studies. Okay, and so how do we classify chemical toxicity then? We have three different classes. Very toxic when the LD50 value is between 1 and 25 milligram per kilogram body weight. If a chemical has an LD50 value of say 10, that is supposed to be very toxic. And the next class is toxic, which has a value between 25 and 200, 25 to 200 milligram per kilogram body weight. And harmful, of course, is 200 to 2,500. So this is how chemical toxicity is classified. How about routes of entry of toxins? Toxins can enter the body through a number of routes of exposure. The most important is oral. The gastrointestinal tract, it's basically designed to absorb a variety of chemicals. It cannot distinguish food molecules from toxic chemicals. So toxins are absorbed, toxins that are absorbed are first transported to the liver, from where they are transported to the other parts of the body through the bloodstream. So it's quite likely sometimes, many times these chemicals get altered by the liver. And there is also a possibility that these chemicals may get detoxified. The other two routes are lungs and skin, and these are not that important as far as food safety is concerned. Okay, this route of entry is not quite important, and toxins that enter lungs must be either volatile gases or dust. Skin, again, it's a very effective barrier, and not many chemicals can get through skin, so we will not talk much about this one. Okay. So what happens after entry into the body? These toxins, they are transported to the tissues. Okay. And normally this is achieved through the bloodstream. Okay. Once the target tissue has been reached, the toxin must have the ability to cross cell membrane in order to damage the cell. So these molecules are very, very small in size, and they very easily pass through the membranes and damage the cell components, actually. Okay. In cases where the chemical does not pass from the body without change, the body chemistry can alter the toxin by a number of reactions called biotransformation. When you have these toxic chemicals in the body, they can get transformed through a number of enzymes and other chemicals in the body, actually. So these reactions are most likely to occur in the liver. That's why liver is called the chemical factory of human body. And as I mentioned to you just a few minutes ago, they can also get detoxified in the body. And I'm going to give you a few websites, and these are really important in the sense when you develop your hazard plan, it is vital that you make use of good information, the quality information, and you can obtain this information from these three websites. Actually, they, in fact, I think they keep updating the scientific information on the hazards, their routes of entry, and their mechanisms, and all that. Everything is updated. I mean, these are good websites, actually. Another excellent source of data on human hazards associated with ingredients and chemicals. It's really important for the food industry, and that is your safety data sheet, SDS. So under legislation, you all know that suppliers of specific materials, chemicals, and other substances are required to provide these data sheets to users of their products. And I'm sure you have gone through some of these safety data sheets. So when it comes to risk assessing chemical hazards for food safety, you need to consider a number of specific areas, actually. So these are the specific areas. What are those things? One, exposure assessment, daily intake. what is the extent of exposure of these toxic chemicals, and what will be the daily intake and things like that. And then we just discuss about dose response data. So you have to have some information about dose response data. And toxicity testing data from humans or animal data for extrapolation. So again, you'll have to depend on scientific information. ADI data is nothing but acceptable daily intake data. Again, this is available in the scientific literature. Mechanisms of action of toxic effects. And how does these chemicals act inside the body? So you have to have some idea about these things actually. So in practice, obtaining all this information may be time-consuming sometimes, and sometimes may not be available, or requires a lot of technical expertise. In such cases where either expertise or resources are not available, so you may make use of a consultant, so that will help you to develop a robust hazard plan, okay, based on chemical hazards. Now let's look at the various categories of chemical contaminants. 99% of all toxins are naturally occurring, and also that all things are you must know that not all things are toxic at sufficiently high concentration. Many food raw materials contain chemicals which, if consumed in excess, might lead to health problems. We are aware of that. We all are aware of that. Generally, cooking and processing can remove or inactivate many of these chemicals. I'll give you some examples. Protease inhibitors, lectins in beans, protease inhibitors in soybeans. So these are some examples by which you can inactivate these chemicals actually. Or there may be some chemicals that are really naturally occurring, but that cannot be detoxified easily. Okay, I'm just going to give an example. One recent example is a process-derived chemical hazards for its formation. I'm referring to acrylamide in baked products. So though this has been occurring for centuries, and this is nothing new actually, this has been occurring for centuries. Example, I think in home baking of bread, potatoes, and starch-based foods. It was going on forever, but this was not discovered until 2002. Okay. And again, another area of concern is the migration of chemicals from packaging materials into food, which has recently become a large problem for food manufacturers. So, as food manufacturers, you should know what's coming from your packaging materials. Is there any possibility, is there any risk of chemicals migrating from your packaging materials into food? So you should be aware of that, and then you should have identified that in your hazard plan and appropriately documented that. Okay. Other hazards that could be introduced by accident during production of the food raw materials. I mean, it could. You can also apply that to food raw materials. Sometimes these are unavoidable, and yeah, how does it occur actually? It occurs because of poor growing practices, post-harvest practices, and sometimes inappropriate processing conditions. Okay. Mycotoxins produced by mold or molds on grain are not products of, they are examples of this particular category. Okay. Again, nitrate accumulation in leafy vegetables and heavy metal accumulation in seafood are other examples of this category. Okay. But the most difficult one to control are the chemical hazards introduced deliberately. Okay. Intentional adulteration, intentional contamination. Generally, this is as a consequence of fraudulent trading. Okay. An example is melamine in milk. This was a big scare some years ago. People added melamine to milk to boost the apparent protein content. Okay, so chemical hazards can, therefore, we can categorize chemical hazards into 5 broad categories. 1, natural toxins or inherent toxins. 2, natural and environmental contaminants. 3, process and storage derived contaminants. 4, deliberately added contaminants. And the last category is pesticides and veterinary residues. Let me go through the categories one by one. I'm going to provide a lot of information about these hazards in detail. Okay. The first one is inherent toxins. These toxins, these chemicals occur, they occur as regular constituents of food in question. Example, lectins in kidney beans, or they may also get produced at increased levels as a response of the foodstuff to some sort of stress. Even plants undergo some sort of stress. Animals also undergo some kind of stress. Okay, an example for this, increased level as a result of response of the foodstuff to stress is glycoalkaloids in potatoes. Okay. Because this particular chemical, there is an increase in concentration when the tuber, when the material is exposed to light. Okay, so these are some inherent natural toxins. There are some instances of processing regime potentially releasing a toxin from a non-toxic material. Okay, I can give an example of that. Cyanogenic glycoside in some canned stone fruits. I'm not sure you are familiar with ackee fruit. Ackee fruit in the Caribbean is an example of that. This can also be considered under the process-derived hazard, but essentially this is natural because it gets formed when the plant or the material is subjected to some kind of stress. Lectin. Lectin, this particular toxin, occurs in a wide variety of plants, including kidney beans, lima beans, broad beans, castor beans, soybeans, you name it, even in lentils. In many cases, lectins have no appreciable toxic effect. That doesn't mean it's not toxic. In many cases, it doesn't produce toxic effects, but it can also produce toxicity. It can also lead to toxicity when the concentration is adequate to create problems, actually. Okay. The most well-known example of this is red kidney beans. Okay. And raw kidney beans are significantly toxic due to the presence of lectins, and that's why I think this bean, red kidney beans, must be cooked adequately before consumption. Otherwise, you'll experience high level of toxicity. Okay. I just mentioned to you about glycoalkaloids. That's the second bullet point here. Okay. Potato glycoalkaloids are a good example of naturally occurring toxin, and this can cause real problems at times. Okay. Potatoes, in fact, contain 2 main glycoalkaloids. One is solanine, and the other one is chaconine. Okay. And chaconine is more toxic. Okay. Symptoms may include abdominal pain, vomiting, diarrhea, etc., etc. And mean, there's an accepted safety limit for chalconine, and that is 200 milligram of this per kilogram of fresh potato. Anything above this level is supposed to cause toxic effects. Again, the increase in levels of these glycoalkaloids occur because of a number of factors, including stress factors such as, pest and disease damage, drought, extreme temperature variations, etc., etc. This is prior to harvesting, and even post-harvesting. The way you handle these materials, abrasion, etc., etc., mechanical damages, all these things will lead to stress, and that will result in increased levels of these glycoalkaloids. And the third one is oxalate. Okay. Oxalic acid, some of you may be familiar with oxalic acid, and these are oxalic acid and oxalates are widely distributed in plant food, okay? And you may find very high levels in spinach, about 0.3 to 1.2%. Also in rhubarb, okay, cocoa beans. Although there is no question that the ingestion of high levels of oxalic acid can be fatal, there is no doubt about it, okay? But there is considerable debate as to whether serious food poisoning from oxalate is usually due to food. Okay? It's widely present, but there is a bit of controversy there. Okay? But as far as, there's some consumer perception also. Eating rhubarb leaves, that has been a well-known cause of illness for centuries, actually. Okay, because these leaves contain high amount of oxalates. Okay. Let me talk about cyanogenic glycosides. Many fruits and other plant foods contain compounds that have the high potential to release cyanide. Okay, you're all familiar with cyanides. These compounds are basically glycosides. That means they contain a sugar molecule linked to cyanide group. Okay, and the release of cyanide group from these compounds, they occur by enzymatic hydrolysis. Okay, usually when the plant tissue is crushed or otherwise disrupted, because then the enzyme gets released, enzyme acts on the glycoside and releases cyanide, then it becomes a poison. Okay, but it can also occur in the digestive system after the food has been eaten. Okay. Example, bitter cassava, etc., etc. Let me talk about trypsin inhibitor. Okay, these are examples of inherent toxins. This is the first category of chemical hazards that we're talking about. Trypsin inhibitor, these are substances which have the ability to inhibit the proteolytic activity of certain enzymes, which are found throughout the plant kingdom, actually. Examples, lima beans, soybeans. Most of these inhibitor compounds or substances, they're basically proteins, and they get inactivated by heating. So cooking is an important step. So cooking will not only increase in nutritional value, but they may also destroy some of these chemical hazards. Let me move on to the next slide, that is natural contaminants. The most important thing is mycotoxins here. Mycotoxins are basically substances produced by a range of fungi or molds. And they have toxic effects on both humans and animals, and they range from acute toxicity and sometimes even death. Okay? They may also impair or suppress immune functions. They may lead to tumor formation. They may lead to cancers and all kinds of chronic diseases, actually. Okay? The mycotoxins of interest here, they're mainly produced by mold species, basically the three mold species: Aspergillus, Penicillium, and Fusarium, actually. Okay? And these are mainly storage molds affecting commodities such as nuts, dried fruits, and cereals. Basically improper storage practices, etc., etc. Let me just get into the details of individual mycotoxins. The first one is aflatoxins. Aflatoxins are produced mainly by some strains of Aspergillus flavus or Aspergillus parasiticus. Basically, there are four main aflatoxins: B1, B2, G1, G2, plus two more. They are M1 and M2. The aflatoxins are potent liver toxins in most animals and also carcinogens. Okay. Aflatoxin B1 is probably the most toxic and carcinogenic. Okay. And aflatoxin production is very high in warm temperatures. When the temperature and humidity are favorable, these molds produce these toxins, okay? Particularly in the tropical and subtropical regions, on corn, peanuts, cottonseed, tree nuts, etc., etc. The other interesting one is acrotoxin. This is a group of compounds produced again by Aspergillus species, but a different, again, Aspergillus genus, but a different species, actually. Okay. The main toxin in the group is acrotoxin A, which causes liver damage, which is scientifically it has been found they cause liver damage in rats, dogs, and pigs. Okay. And they can also be teratogenic, meaning to the small babies, actually. Okay, even before ingestion may lead to a lot of problems before birth. And now these acrotoxins are thought to be carcinogenic in human beings also recently. Okay. Now something about patulin. Patulin is produced by, again, Penicillium and Aspergillus species. The most common producer of patulin is Penicillium, and the species is expansa. Okay. This occurs primarily in rotting apples, okay, in the production of apple juice, for example, and that's why, production of apple juice, you would like to verify the content of patulin. Patulin is toxic to many biological systems, including bacteria, higher plants, and animals. Okay. The other chemical hazard that is natural contaminant is zearalenol, and this is also known as F2 toxin. Okay. And this is produced by several species of Fusarium. Okay. And this occurs naturally in high moisture corn, and mainly from the growth of this particular mold, actually, Fusarium. Okay. Again, production of this compound or chemical is favored by high humidity and low temperature. Yeah, particularly during harvest, actually. These conditions are quite conducive to the growth of these molds and then the production of these toxins. Okay. The other one is trichothecenes. These are a group of some 20 chemically related toxins produced by Fusarium species. Okay. And some of you may be familiar with the occurrence of DON, DON, which is otherwise known as deoxynivalenol, okay, and short form is DON, which causes vomiting in animals, and hence the name, it's also called vomitoxin, okay. It has been found to be a teratogen, and this is found in commodities such as corn and wheat. The other one is fumonisins. Again, this is a group of compounds mainly produced by Fusarium species, Fusarium proliferatum. Okay. And this has been linked to several diseases, including liver cancer, esophageal cancer in humans, etc. So I think there are some scientific information about the toxicity or the after effects of these chemicals. I'm just going to quickly go through shellfish toxins. Okay? There are several types of shellfish poisoning, including neurotoxic, paralytic, amnesic poisons, actually, all coming from shellfish. As a matter of fact, these toxins are not produced by the shellfish themselves, but they're accumulated through the ingestion of planktons, because when shellfish consumes water, water contains a lot of planktons, and plankton is a food for shellfish. So when it goes through the body of shellfish, these things get filtered out, and this is the source of all these chemicals, actually. Okay? In fact, paralytic shellfish poisoning is a global problem. Okay? These toxins can persist within the shellfish at dangerous levels because these shellfishes, they consume a lot of planktons. There is a possibility of very dangerous levels of these chemicals getting accumulated in the body. Again, there is another kind of shellfish poison called amnesic shellfish and all that. So I'm not going to go through. You may find a lot of information in the literature. Okay. The other one is, I think, Sugatera fish poisoning. This is an intoxication caused by the consumption of coral reef fish, which feed on certain marine plankton. And obviously, these planktons contain specific toxins. Okay. These are some of the common marine food poisoning worldwide. It's not only in North America, it's a global problem. And they create significant health problems. Yeah, so we went through all the detail. This slide shows different types of aflatoxins, acrotoxins, pathogen, zearalenone, trichothiazines, and fumonisins, etc. Okay. Let's talk about some environmental contaminants. The first one is dioxins, polychlorinated biphenyls, okay, commonly known as PCBs. PCBs and dioxins are persistent contaminants with a range of chemical structures, not just one chemical, a multitude of chemicals. When we say PCB, it contains several chemicals, actually. They have been found in soil, water, sediment, plant tissues, animal tissues, you name it. Okay? And interestingly, they have long half-lives. So that means they're quite persistent in the environment, and they have obviously toxicological effects in human beings, in humans. Where do they come from, actually? PCBs and dioxins are man-made chemicals used by industry, for a variety of applications. And inadvertent release of these chemicals to the environment is generally the source of these chemicals. I can give you some examples. So these products are formed when there is fire, or they can also get formed during some manufacturing processes. there are reports that these are virtually present in all foods, and these are getting ingested into human body. Okay, the highest concentration are in fatty foods such as oily fish, and the main source of dioxins. I mentioned two chemicals. One is polychlorinated biphenyls and dioxins. So dioxins are present, or may be present, in the diet, basically meat and milk. Okay, and these levels accumulate as they move through the food chain. Okay, because we are at the end of the food chain, human beings may have the highest level of these contaminants. So what are the control options then? The control options are based on prohibiting the use of dioxins and PCBs by the industry. So, and when the use of these chemicals are controlled, obviously the release of these chemicals to the environment, that is also controlled, and incidentally that is going to reduce the contamination level in foods. Okay. Unfortunately, no limits exist here, but FDA's opinion on this is any detectable level is considered to be a matter of concern as far as FDA is concerned. Okay. I'm continuing with environmental contaminants, and here we are going to talk about polycyclic aromatic hydrocarbons, actually, also known as PAHs. Okay. These are a group of compounds comprising of two or more aromatic rings, and that's why polycyclic aromatic hydrocarbons. Okay. One simple example is naphthalene, and a variety of toxic properties have been related to PAH, polyaromatic hydrocarbon exposure, including the capacity to produce carcinogenic effects in mammals, actually. Okay. And where can you find these chemicals? PAH, for example. They are found in petroleum and coal, and they can also be formed by the incomplete combustion of these organic materials. Okay, and these compounds have been detected in air, water, soil, and food. Food may become contaminated through direct exposure, or sometimes migrating from packaging material, or also during thermal processing of food. I can give you an example: baking, grilling, frying, smoking. All these process steps may lead to the formation of polycyclic aromatic hydrocarbons. Okay? But when we talk about fruits and vegetables and cereals, it's primarily through soil and air exposure. Okay? Shellfish can also accumulate polycyclic aromatic hydrocarbons. The other one is direct fire drying and heating process used in the production of food oils can sometimes result in high levels of polycyclic aromatic hydrocarbons. The specific foods of concerns, the specific foods of concern are primarily fish, which are fried or are formed in oil-contaminated waters. If you have oil spill and all that, then you'll find high levels of these polycyclic aromatic hydrocarbons. Something about heavy metals. You're all familiar with the common heavy metals such as mercury, cadmium, lead, arsenic, etc. These are basically natural components which originate from the Earth's crust and are found all over the world, actually. Okay. And these have been recognized as health hazard for many years. And they can occur in a variety of foodstuff of both plant and animal origin. Crops, fish, milk, you name it. Lead is a widespread contaminant. It's a pollutant derived from human activities such as lead mining, smelting, and processing, and also burning of fossil fuels. These are the sources of lead contamination. Okay? And the main route of crop contamination is uptake from the soil, actually. Maximum levels for heavy metal contaminants or contamination have been established in many countries. So it's important for us to know the legislative limits when you try to export your products, actually. Yeah. Each metal has a specific limit, which is again food type dependent, and a lot of information is available in the literature, actually, about the after effects of consuming heavy metal contaminated foods and all that. Okay. Something about process-based contaminants. The production of toxic chemicals in foodstuff through processing is a recently discovered phenomenon. Okay, although this has been occurring for a while, things are coming to light only now. Okay. I'm just going to give some information about acrylamide because that's the most well-known example of process-based contaminant. Okay, I think somewhere in 2002, Swedish scientists unexpectedly discovered this when they were carrying out a study into occupational exposure of acrylamide. And subsequent research has revealed that this particular chemical is formed in food by traditional cooking methods such as baking, frying, roasting, etc. When you roast materials at high temperatures, this gets formed, actually. Okay, and examples of foods that are at risk are potato products such as potato crisps, chips, coffee, savory snacks, like particularly cracker-type biscuits and bread and cereal products. These are some products where you may find high levels of acrylamide. Okay. Again, something about chloropropanol, which is again not that well known, but these are also potent process-based contaminants, actually. Okay. And these chemicals you may find at low levels as a result of processing or migration from packaging materials during storage, or even domestic cooking may also result in the formation of these chemicals, chloropropanols. The other one is furans. This is a colorless volatile liquid, and this is used in some chemical manufacturing industries. Okay, and occasionally you may find these chemicals in food. Okay. And also during heat treatment techniques such as cooking, bottling, canning, etc., they may also lead to the formation of furans. Well, something about packaging materials. There is a risk with any packaging materials that some of the components of packaging materials may be transferred to the food that it is surrounding. Packaging, in fact, I think they're basically chemicals, and in most cases, the level of transfer is extremely low, but that doesn't mean they don't occur. The variety of chemicals have been found in food products as a result of migration. And transfer of monomers and additives such as plasticizers, plastic packaging materials, these are the major areas of concern. Okay? Again, there are limits. The general limit for containers and sealing devices is 60 milligram per kilogram of food. For other food contact materials, it's 10 milligram per decimeter square. I mean, there are some European regulations, and there are some regulations locally also. And let me talk about deliberately added contaminants, otherwise known as intentionally added contaminants. There is no limit to what chemical contaminants might be deliberately added to food during manufacture in order to cause harm to the consumer. In most cases, the aim is not to cause harm, and the primary intent is not to cause harm, but to defraud for financial gain. Okay, but what happens, the damage is already done. Potential harm does exist. Okay, one example I can give you: the Sudan group of chemicals. I mean, these are synthetic dyes, colorants actually, and people added this. I mean, this is also used in products such as shoe polish, automotive paints, etc., etc. Unfortunately, someone used these dyes to chili powder, to give it a better color. And these are definite toxins actually. And the other example, you all know very well, is melamine. Melamine is an industrial chemical found in plastic. Okay, I mean, I don't have to get into the chemistry of that, how melamine gets produced, but some time ago this was used to boost the level of nitrogen in milk. And obviously that resulted in the death of a number of infants in China, actually. So, and not only that, not only in milk powder, this was also found in pet foods. Again, that created a big scare here. And, there's a big legal case on that. So, it has absolutely, as I said, no nutritional value, but it has got high nitrogen content, and that's why this was added intentionally to get a higher level of protein. And obviously, I think this is higher protein level is linked to the sale price of milk, and that's why people added melamine to get a higher price for milk they were selling. Pesticides and veterinary residues. Okay. Pesticides include chemical and biological products specifically designed to control pests, weeds, and diseases. Okay. Particularly in the production of food, and a variety of pesticides. Some are insecticides, some are fungicides, some are herbicides, some are rodenticides. Okay. In fact, these are highly regulated in many countries, and even the application is highly regulated. Okay, but still misuse is taking place in many parts of the world. Okay, there are regulations that include restriction on the target organism, the chemical that's used, and the concentration of pesticides to be used. Everything is highly regulated. When we talk about insecticides, basically there are three classes, three families, you may say. That is organochlorine, organophosphorus, and carbamates. The toxicities of these chemicals vary greatly, but these are organochlorine was extensively used in agriculture long ago, but many of these chemicals have been banned in North America. But because they have a long shelf life, you may find concentrations of these chemicals in food because they have already penetrated into the food chain in many parts of the world. Okay, because organochlorines are lipophilic, meaning they love fat and they get attached to fat molecule. And as long as there is fat in food products, you will find organochlorine pesticides or insecticides in food products. Okay. Again, that has led to a lot of problems. These are neurotoxic. Some of these things have direct effect on the nervous system, actually. Okay, and the other class of pesticide, organophosphates, they disappear in the environment quickly, but they are potent poisons. And now these days you have less toxic insecticides. These are called carbamates. Okay, and there is a trend to use natural insecticides, natural chemicals to control insects and pests, actually. Okay. Now, how are maximum limits set, actually? Okay, there are these chemicals. All these chemicals we talked about, they could enter food chain. Okay, some of these are unpredictable because they are deliberately added, but most can be controlled. Okay, the main route the main route for this is good manufacturing practice, and monitoring of environmental conditions and the quality of incoming materials, such as your raw materials and ingredients, will definitely play an important role in reducing the level of these contaminants in your materials and also in your products. Okay. When the limits are set, people normally look into these things. The toxicity evidence. How toxic is the contaminant? And something related to good manufacturing practice. So what is technologically available? How costly is it? These questions are asked before people decide on the maximum levels. And also analytical capability, and every day the analytical capability is improving. People are able to detect parts per trillion level of chemicals in a variety of substrates, including food products. Okay. Now, the last couple of slides on codex limits, that is 24 and 25, that's purely for your information, actually. Codex has set limits for a variety of chemical contaminants, mycotoxins, heavy metals, and all that. So I've given the information on slide 24 and 25. And that's about it, and thank you very much. And if you have any questions, I'll be more than welcome to answer your questions. It appears there are no questions, and then I'll have to thank you all for your time, and good luck. Thank you. Bye.